In this video we're going to look at creating an eyelid setup using geometry nodes in Blender. It's fully procedural, has loads of features and it's pretty robust. I've used it in production myself and hopefully there's some stuff in here you find useful. Okay, let's get started. Let's start by creating the geometry we're going to need for our eyelid object. So a geometry nodes workspace, create a new geometry nodes graph, drop down a new cube primitive in here, and the reason for that is so that we can have access to the resolution. So let's start straight away by creating a new input on our node graph, give that a better name, and we can use that for all three axes. Let's increase this and turn on a wireframe overlay. So let's just come in here to side view for a second. What we want to make sure is that we've always got a nice edge loop running through the middle of our object. You can see we do at the moment, but as soon as this resolution input becomes even, we lose that central edge loop. So to make sure we always have an odd number here, we're going to multiply this by 2, and then that will always give us an even number. And then by adding 1 to the result of that, we'll always end up with an odd number. A slightly more descriptive name, this is going to be times 2 plus 1. Let's frame this up and keep things neat from the start. The next thing we need to do is we want to create a split in this mesh where the eyelid can open and reveal the eyeball inside, and we want to split from this point where the central edge meets the X axis. We're going to come around the front of the object to the same point on the other side. So if we take a position node, separate this into its XYZ component, we want edges where the Z position is exactly 0, which means it's lying on the XY plane. So Z equals 0. And we also want points where the Y axis is less than 0. The positive Y axis running in this direction, we want to split these edges here. So Y is less than 0. These are our two criteria. If they are both true, put this through an AND Boolean math node. If they are both true, we want to use the result of that to split edges. And just to confirm that this is working, we can drop down a set position node, take the existing position and blur it ever so slightly, and we should see we have a nice opening now where eventually we'll be able to peel these lids back to reveal the eyeball inside. Frame this up, edges. Next, let's turn this into a slightly more spherical shape so that it resembles an eyelid. So we drop down the position node, we normalize that vector. This should give us a sphere with a radius of 1 unit. And the next thing we need to do is we want to store from this reference vector how far do we need to rotate in order to reach each point on the mesh. So we're going to take its position, we're going to multiply by 0 in the x-axis because we're only interested in its position on the ZY plane. So x is 0, we're going to multiply y and z by 1 so they don't change. So we want to align this new position vector to the y-axis and measure how far we've had to rotate in order to do that. And then we want to examine the x component of that rotation because we're twisting around this x-axis down towards the y. So let's drop down a store named attribute, call this something like rotation multiplier, rot_mult. It's going to be a float, it's going to be on the point domain. At the moment, because we're dealing with rotations, this is going to be a value in radians. It's going to run from negative pi all the way around to positive pi. So 2 pi radians gets us all the way around 360 degrees. We want a range between 0 and 1 ideally. So we're going to map this value from negative pi to pi, store that, and let's just quickly have a look at what it's giving us currently. As you can see, we get nice values going from 1 on the top lid, gradually decreasing all the way down to 0 on the bottom lid. And the problem is we're not getting a separation along the edges that we've split. Now we can easily fix that by just blurring the position attribute that we're measuring from by a very tiny amount. 0.01 should be plenty. If we replace that, you should see that we now get this nice harsh separation between 0 on the bottom lid and 1 on the top lid. Let's frame this one up. Okay, so now we should be able to actually open this up and test that we've got everything working so far. Let's take their position, put that through a rotate vector, We're only interested in rotating on the x-axis, so do a combine, and then on the x, let's just create a math node. We're going to multiply, so we want a named attribute. Copy that from there, and then what we should see, if we put this into the position, we should be able to manipulate this in order to open up those eyelids. And you can see the vertices are rotating with a really nice fall off, so we can go all the way around, and they never cross over one another, they never kind of crash through each other, so I'm getting a really nice distribution of the movement there. So let's start by creating 6 new float inputs on our group, and let's rename them. So we want one for the overall movement of the top lid, one for just the right hand side and the left, and the same for the bottom. So let's start with the overall top lid. We should be able to pipe this value directly into our existing multiply here, and then that should allow us to manipulate the top lid via this attribute here. Bottom lid is fairly straightforward as well. All we need to do is, if we take one and subtract our rotation multiplier from it, that by the lid bottom attribute, and what we're going to end up doing is adding lots of these multipliers together. So if we add those two together, the top and the bottom lid contributions, we should now be able to manipulate the lids as a whole, top and bottom. Okay, let's work on being able to shape these so that we get a slightly more interesting curve along the lid if we want it. So if we take the position, separate, we're interested in the x in this case, and we want to go from -1 to 1, and output as a 1 to 0. That will give us 1 on the right hand side, 0 on the left hand side. So let's label this, and let's duplicate that while we're here. Definitely going to need the other side as well. Left to right. All we need to do is flip the outputs from 0 to 1. So let's take our right to left gradient, multiply it by our lid top right attribute, and let's add to our global top lid attribute. And let's use this combination in our multiply instead of just the top lid. We have some control over the right hand side of our top lid. Now this fall off doesn't quite look as smooth as I was expecting. Let's check why that is. Oh, I forgot to put -1 into here. So once we add that, we should see we now get a nice smooth curve from right to left. Let's just make sure I didn't do it here either. -1 to 1. To do the left hand side, dead simple, we just multiply the lid top, the left attribute, by the left to right gradient, and then drop in another add, and now we have control over both the right and left hand sides. So let's just frame this up, and if we duplicate all of that down for our bottom lid, we can just swap these inputs over now. So top lid R, we want bottom lid R, top lid L becomes bottom lid L, and bottom lid. Now we can't just add the contribution of the top lid and the bottom lid together, because for the bottom lid we want to actually invert this, so we need to do a 1 minus the multiplier. So we do a new multiply like so, and we put the add after the multipliers. So now we should see we've got bottom lid control, both left and right, separate shapers, and same on the top. So let's work on being able to blink this eyelid such that the top and bottom lids create a really nice precise seal. So we're going to need to add a couple of new parameters to our group input. They're both going to be floats, and they're both going to have minimum of 0 and a maximum of 1. Let's call them blink, and the second one is going to be blink height. So here we have the result of the top lid contribution, and we want to create an alternative to this that switches to being controlled by the bottom lids. So let's duplicate this multiply node. We want the same multiplier, So we want the raw rotation multiplier. But instead of taking the top lid contribution, this time we're going to take the bottom lid. And then the same here for the bottom lid multiplier. We duplicate that. We want the inverted influence still, but instead of the bottom lid contribution, we're going to take the top. Create a mix between each of these two multipliers, like that. And as we do this, the lid closing, because we're now blending the top lid halfway towards the bottom and the bottom lid halfway towards the top. So what we want to do is equalize these two factors so that they always add up to 1. And the way we can do that is to use our new blink height attribute. When blink height is 0, we want the bottom lid to stay in its position. So we want this factor to be 0. We can plug that straight in. And we want the top lid to blend all the way down to the bottom lid's position. So we need to do a subtraction here. 1 minus blink height. And now what we should see is that no matter what we do with this attribute, the lid will always stay closed. Even if we add some to any of our attributes, they will always line up. But now we can't open the eye, so we need to create one more set of mixes. And this one's going to go between our sealed eye that we've just created. That's going to go into input B, and our open eye, which was this first one here, into input A. And then the same for the bottom lid. Our sealed eye into input B, and our original one into input A. And the factor for both of these mix nodes is going to be our blink attribute here. So let's just swap these into our addition. We should go back to our open eye, which is in a bit of a weird pose at the moment, but that shouldn't matter. We should be able to start from any pose. And when we blink, the lid should come together perfectly like that. We can change whether the blink happens at the position of the lower lid or the upper lid. Using our blink height, they should always seal. So this is getting a little bit confusing in here now. I'm just going to add a few labels to tidy things up. Okay, so next let's work on the ability to rotate these corner points of our eye opening around the Z-axis so that we can bring the opening round to the front, cover less of the sphere and create a smaller, beadier eye. Or we can rotate them right around the back to create more of a clamshell kind of cartoony look. So what we're going to need to do is, we'll obviously need another set position node eventually. Take the position of the vertices, separate. We want to do a rotate vector. The vector is going to be the position, and the rotation to make a new vector by combining. If we plug this in, we should be able to see that by rotating around the Z-axis we can spin these corners. All we need to do is use the x-coordinate as a multiplier for that rotation. We're going to need an input on our group, call it corner width. And let's multiply that attribute by our x component of the position vector. We use that to drive our Z rotation. We should be able to influence the positions of those corner points. It's not quite working because as you can see, when we bring these closer together, we start to get a pinching in the center. At the moment, our x component of our position vector increases linearly from -1 to 1. We want to influence the way that gets mapped using a function called arcsine, which is going to cause the corners to rotate more than the points nearer the center on the x-axis. We should see rounder shape. It's maintaining the characteristics of our original pose much better. Now probably something we also want to do is modify the height of this pose based on this attribute so that it's proportional essentially. So all we need to do back here, after we've added up all of our various lid pose contributions, we just want to multiply this according to our corner width So as we are decreasing the corner width, we also want to decrease the height of this pose. So let's map range, and we want, when the width is at 0, we want the multiplier for this to be 1, because we don't want to change the height. And we probably don't want to change the height as we go back beyond the default. I think it's only when we come around the front that we want to maintain that proportionality. So as we go down towards, let's say -1 is completely closed. Let's put -1 as our from max. What do we need this multiplier to be? Well, let's plug it in and just have a play around with the range and see where we get to. Let's set it to something a little bit less extreme. Continue to bring this down until it feels like we're maintaining the pose. Maybe 0.05. And we should see now that as we increase this, it feels like the same shape, but just shrinking on the surface. And all of our blink controls still work as we expect. We can still open this as wide as we want. So let's frame up. Okay, next job. I think it would be nice to have the ability to manipulate the height of these corners so that we can have more of an almond shaped eye where the axis isn't exactly horizontal. All we need to do is duplicate this entire frame. We could probably do it all in one, but I like to stack these operations one after the other in series, and then I think it's more predictable. So let's add a new attribute to our group. This one's going to be corner height, and we're going to separate these into left and right this time, so we're going to need one for both. And it's pretty much the same setup as the corner width. Let's just change that label so we don't get confused. The only thing we need to really change is that the rotation is happening not on the Z axis this time, but on the Y. So if we change this to the Y axis, and instead of corner width, we're going to control it with our new corner height attributes. Just do the right for now. So it just remains to split the left and the right side. This is very similar to what we did with the lid posing attributes. We're just going to add a duplicate of this multiply. We're going to swap it for the corner height left, and we're going to add these together to give us our separate control. At the moment you can see this is still influencing both sides. So what we need to do is let's create a little bit of extra space. Let's take the X, which currently goes from -1 to 1. We'll map the range from -1 to 1. We're going to go from 1 to 0. This is going to be our right to left gradient, so we want to use that as the multiplier for our corner height right attribute. And then let's duplicate these down, swap the outputs from back to 0 to 1, and we'll use this as our multiplier for the corner height left. So now we should be able to control each corner. Everything should still work. I think the next thing we want to do is add some thickness to the eyelid. So fairly simple, we're just going to use an extrude mesh. We want to extrude faces. We do not want individual extrusions. We probably do want control over the thickness of that extrusion. Let's add a group input, yet another attribute. We'll call this one thickness. And I think it would be also useful to store the row of faces on the inside of this in case we want to darken that area off in the shader, for example. We'll call this rim. We'll just make it a boolean. We'll use the side of the extrusion. Let's just add a sphere to the scene to use as an eyeball. Let's add a couple of materials just so that we can get the idea. Add a material for our eyelid as well, and make sure we assign that through the modifier. We could also add a level of sub D to this just to give us a nice round edge, and there we have it. Fully posable procedural blink, control over upper and lower lids, the width of the corners, and of course if you want a non-spherical eyelid you can scale any way you like and it will still work properly as long as the scaling is done either at the object level or in a modifier after the geometry nodes. So this is just going to be a quick bonus. We're going to look at creating some procedural wrinkles that happen on the eyelid as the eye opens and closes. I think it's a good example of how versatile these geometry node setups are, because the first thing we're going to do is change our input geometry from a cube to a UV sphere. And the reason for that is, if we look at our current geometry, the loops that are running around the geometry are not flat. They've got these kind of baked in dips in them, which get more extreme the further up we go. And this is just down to the topology of the cube we used to start with. With a UV sphere, we plug that in instead. We can see now these loops are nice and flat all the way across. And the eye still works exactly the same as it did before, with completely different topology. So it's a really versatile setup, this. You do have these poles on the top and the bottom which can cause pinching, but I figure you're not going to see the top and the bottom of an eyelid very often, so for me it's worth it for this extra functionality that we're going to be able to build. Okay, so the next thing we need to do is, before we split the edges along this ring, we're going to just store an attribute. Get rid of this cube, we don't need that anymore. We also don't need this +1 anymore because we're using an even number now. So we want to store a named attribute. It's going to be a float on the point domain, and we're going to call it wrinkle. Basically, what we want to do is, for each alternate edge loop, we want to store a value of 0, 1, 0, 1, 0, 1. Now what I tried initially was to use the Z position of these edge loops to kind of separate them out and get that attribute working. But actually the gaps between these edge loops get smaller as we go up towards the top of the sphere, so that approach didn't work. But if we look at the UV map of a UV sphere, you can see that here the edge loops are nice and evenly spaced. So if we pipe the UV map out, we're going to separate X, Y, Z. It's the Y we're interested in, which is the vertical axis on the 2D UV map, and we want to map the range of that to a different space. We're going to be using a sine function to get the alternating values between 0 and 1. So the period of a sine wave is 2 pi. It's a full 360 degrees. So we want our 2 max to be 2 pi. You can type tau and that'll give you that value. And for the inputs, we're going to base things off our resolution. So no matter how many times we divide the sphere, we've always got the right allocation of attributes. We take our resolution. We're going to multiply it by 0.5 because you only want to deal with every other loop, and then we want to divide the result of this by the maximum distance above the ground that our sphere achieves, which is going to be 1 meter. That's the radius. So divide, we're going to do 1 divided by half our resolution. That's going to be the from max in our map range. And now we can plug this into the sine function. We want the absolute value. A sine wave looks like this, goes up, down, and it crosses the 0 line. We don't want that, we only want the positive, so we want to turn this into an absolute value. And then before we plug that into our attribute, we want to multiply it by the distance along the y-axis of our points. We want it stronger at the front edge and tapering off as we go back towards the center line. So if we drop down a position, separate X, Y, Z, we're interested in the Y, but because our eyeball faces down the negative y-axis, we want to multiply this by -1. And now if we multiply our absolute sine result by this value, we should be able to store that in our wrinkle attribute. Let's just double check that that's working with a named attribute. And now we can see we're getting a nice 1 to 0 alternating value which tapers back to the center line. And if we increase our resolution, we maintain that alternating pattern. So let's just frame, and then we're going to come right to the end, and this is where we're going to use that attribute to displace our geometry. And we want to be pushing out the wrinkles along the normal, and we want to scale that value by the wrinkle attribute that we just made. If we plug that in now to the offset of our set position, it's going a bit crazy. And I think that might partly be because we haven't clamped something back here, so we're getting values beneath -1. There we go. So this multiply on our -y, we want to clamp that so that none of these values back here get affected. So obviously this effect is way too strong, and we're going to need to modulate it with some other attributes. And the way we're going to do this is we're going to use a change in height to determine how much we want to wrinkle. So as the points get pushed up higher, we get more wrinkling. Or on the bottom lid, we're going to invert that, so the lower we go from the original position, the more wrinkling we get. So we are going to need to store another attribute right at the start, which will be the original position. So let's put a store named attribute here at the very beginning of the graph. It's going to be a vector, and it's going to be the position. We'll call it orig pos for original position, and then we can reference this back here with a named attribute node. So if we separate this, take another position node, separate that as well. We're interested in the Z position of both of these, and we want the difference. So if we take the original position, subtract the actual position, we'll get the difference between those two. And this is going to be for the lower lid, I believe. We'll need to swap the order of these subtractions to get the correct result for the upper lid. So let's get it working for the lower lid first. We're going to put this through a map range node. We can tweak the actual values that we want to our taste. So let's scale this vector once more by this new map range node. And now we can see in our default position we're not getting any wrinkling anymore, so that's promising. Let's try lowering the bottom lid, and as we can see now, as that lowers, we're starting to get some nice distortion happening. And then it's just a case of saying, okay, how far do we want to go before we get our maximum wrinkling? So this value here will be how far do we go before we hit the maximum, and then the 2 max will be the maximum amount of actual deformation that we get. We can probably turn this to smoother step as well to get a bit more of a gradual ease in and ease out. Okay, let's work on the top lid next. I'm going to duplicate this subtract node and switch the inputs, and this will give us our top lid. Let's put in a switch, allow us to swap between these two values, and the Boolean condition for this switch is going to be whether or not the position in the z-axis is above 0. So let's take this z-axis, is it greater than 0? If so, we'll do the switch, and that should be all we need, I believe. If we now crank the lid top, we start to see wrinkling there as well. It's promising. Test it with the blink. So now we're starting to see that the lid top is affected when it goes below the ground plane, and that shouldn't be happening. And I believe that is going to be because, yes, we don't want to reference its current position, we want to reference its original position in our switch Boolean. See, that's got rid of that extra deformation there. So now we only get the wrinkling happening when it's above the ground plane on the upper lid. And the cool thing about this is the more resolution you add, the more wrinkles you're going to get. And it's just a question of dialing these numbers in so that, you know, it's not too extreme. So no matter what shape we make now, these should behave properly. So there we go. That's the full eyelid rig. Hope there was some fun stuff in here and that you enjoyed watching. Thanks for checking it out. I'll see you in the next one. Bye.